Rehabilitation. It's really lovely to be here today. This is a fantastic event. I thought I was coming and I was going to be maybe 100 people drawn from local schools, and this is huge, so it's really, really nice to be able to talk with you today. I think I've been invited to give you some insights about academia, higher education. Why would you want to do that, right? You've been in school for some of you a few too many years, are looking forward to the workspace. There are plenty of jobs available for you. But for some of us, I think pursuing a career in research is actually a really appealing opportunity. And so I'll tell you a little bit of what are some of the perspectives out there, why I chose this, some of the research going on, in particular in AI and robotics, which is my field of study. Some of you might have seen versions of this, right? What is the grad student life like? Might not seem all that appealing. Some of this might seem more appealing than others, but it's not too far from the reality. And the truth is, grad school is a little bit of all of this. And this isn't really the reasons why you choose to go to grad school. This is the reason why I choose to go to grad school. Because for a number of years, I was going to be able to spend my days building robots, playing with robots, and spending time with other people who enjoy doing that. These are all robotic systems on which I've worked over the last 15 years or so. And they're the reason, really, that have kept me in research all of these years. Because about 15 years ago, I was graduating from my undergrad degree, thinking, and I was an undergrad at University of Waterloo, some University of Waterloo, excellent, Systems Design Engineering, class of 98. And in my last year design project, I had the opportunity to work on a 6-legged robot. It was a robot that could sort of walk around. There was 6 legs working in a tripod gait. It was still a work in progress. The robot couldn't quite support its weight once the batteries were all on. So we had some good work laid out for us. I worked in particular on the design of the sonar system. So we had a neat system where sonars were spinning around to try to get a sense of the obstacles in the environment and use that so that the robot wouldn't run into walls and other obstacles. And I really enjoyed the project, but it was a little bit undergrad, low scale, and after that, I decided to go on to do PhD studies at Carnegie Mellon University, which is sort of a great place to be doing grad studies in robotics. And there we weren't limiting to having just sonar sensors. We could have laser rangefinders on our robot, which makes life a lot easier because we get much more precise information about the environment. We can build maps of the environment, get the robot to navigate autonomously, and so on. So the robot you see on the right side over here, something called the NurseBot. That was designed during my graduate student days. And the idea was to build a interactive robot that could do autonomous navigation and was used to help people, elderly people, with their daily activities. So we had some experiments where we deploy the robot in a home for elderly people, where it was spending time there, telling them, for example, when they had certain appointments, accompanying them to their appointments and so on, as well as passing along some useful information. So that was a great time to do robotics, and after about 5 or 6 years of being a PhD student, I'll be honest with you, after 6 years of that, it was time to get out, and I came here to McGill University, where I've been since 2004. And on the left side, what you're seeing is some of the robot systems that we've developed since then in my lab here at McGill, and I'll tell you a little bit more about that later on. So maybe one question you might be wondering is, why should you be doing a PhD, right? Well, it turns out a lot of people are doing PhDs, and the number has been growing from about 2004. Can you see when I use the pointer over here?
Yeah.
Are you seeing it? Awesome. So around 2003, 2004, it was pretty much stable at about 1,000 PhD degrees awarded in, this is US and Canada, specifically for computer science, computer engineering. And since then, from 2003 to 2013, the number has more than doubled, and we're about 2,000 PhD degrees awarded. That's quite a lot of PhDs out there. Right, and wonder, what are they all doing? Are there jobs for all these people? If you look at how the PhDs are divided between computer engineering, computer science, the other science, and other fields, in light blue you have the other fields, and the dark blue is the science, and the yellow is the engineering. So in some countries, the last bar over here, that's Canada, some of the countries we get a lot of PhDs that are not science and engineering, compared to the other side. And in some other countries, maybe Ireland's a good case, more than half the PhDs are on the science and engineering side. We don't have quite as many PhDs. This is the number of PhDs per million people in the country. So we're a little bit lower than some other countries. The United States is over here, and at the other end you have Sweden and Switzerland and so on. But still it's quite a few. It's at about 130 per million for some of the OECD countries. The good news is that despite the fact that there's quite a few of these PhDs graduating, they all seem to find jobs. If you look at the unemployment rate for doctoral degrees, it's actually much lower than if you get just a master's degree and if you get some college and bachelor's degree and so on. So all these people are finding jobs somewhere. Most of these jobs are not in academia. And so that means that there's a lot of research opportunities that don't necessarily involve you ending up as a professor in a university. Depending on what your goals are, that might be a good thing or a bad thing. But there's a lot of opportunities and there's a lot of reasons to do research whether or not you want to go for academia. The earnings are pretty good, right? Not quite as much as if you're a doctor or a lawyer on average, but actually much better than if you're doing a master's degree or a bachelor's, or a little bit better, I guess. And then if you don't have college education. And in terms of where these people are going, I think in Canada, there's a good percentage of researchers that are actually in industry. So for those of you who are going into industry with or without a graduate degree, in fact, chances are that in many of your work situations, you'll be working with people who've done some grad studies, whether at the master's level or at the PhD level. Most of the numbers I'm presenting here are for PhD numbers. It was just a little bit easier to find. I wasn't able to find the numbers for the master's degree, and we can talk about options at the master's level as well. But I figured if I'm talking about academia, let's go all out and think of maybe spending the next 5, 6, 7, 8 years of your life there. So there's jobs for all of these people, a number of them in the business sector. In various industries. There are also government research labs that have job opportunities. Most of the people who do a PhD, though, despite the decent numbers, don't really do it for the money. And the reason is this graph, which some of you might have seen before, that shows your total lifetime earnings. If you don't do a PhD, this is year one after you graduate from your undergrad or master's, and this is where you end up with your lifetime earnings. And if you do a PhD and spend 5 years in academia earning essentially nothing, then the curve doesn't quite catch up. So you shouldn't be doing it purely for financial reasons, right? There should be some other reason why you're going to devote 5 or 6 years of your life to doing research. It's a life that can be difficult. There's a lot of ups and downs in terms of, what your motivation is going to be, how you're enjoying the work. Most people who start a graduate degree are very excited about it, full of optimism. They're going to save the problems of the world. And after a few months of reading papers and talking to their lab mates and so on, they kind of get used to the idea that there's a lot of really smart people in academia working on hard problems, and it's difficult sometimes to make progress. And as you go along, there's a lot of ups and downs. Maybe the worst, though, is like when you've been there for 5 years and you haven't quite proposed your thesis topic yet, and you realize, wow, should I get out at this point? The prospects in industry are actually quite good. The unemployment rate isn't that high. I have a really good undergrad degree. But then you propose your thesis topic, have your PhD defense and so on, and you have a committee of 4 or 5 very smart people who are very excited about the research that you're doing, and so that gives you a little bit of a high. And the hard part is really those last few months where the submission of your thesis manuscript is always 3 months away, and that can drag on for 2 or 3 years for some of us. Nonetheless, a number of people get out every year, graduate. We saw the numbers. Of these people, this is the ones that end up with a PhD, and these are the ones down here who end up with a faculty job, right? So it's a very small percentage of people who actually complete their PhD and then use it to go for a career in academia. And I'll tell you a little bit about what I've done since then. I am one of these people down here who both decided I wanted to pursue a career in academia and was lucky enough to find a position that allowed me to do that. And so I got into Montreal in 2004, showed up at the gates and said, great, fantastic, I know how to do research, let's do this. And over those number of years, what I found is that what's very, very precious about a life in academia is the freedom that you have to explore a diverse topic. Right, so I'd spent 5 or 6 years in my PhD working on a very, very specific, very narrow question. The question was, how do we get AI systems, robots in particular, to make smart decisions? That seems pretty important. In particular, because you have to be precise, right? I'm not the first person to show up and say, I want robots to make smart decisions. So I want robots who are going to make smart decisions in the case where you have to make a sequence of decision, not just one independent decision, but there's going to be some effect between that sequence of decision. The effect of the robot's actions have to have some noise or uncertainty, and the robot has to have only partial information about the world in which it is. And so based on all of these characteristics, we can formulate a very nice mathematical model of how the robot should be making decisions. It involves quite a bit of probability and optimization and so on. And after that, we can actually, once we have the mathematical model, well, it's beautiful. The math lines up very nicely. You can represent a very large number of interesting problems. You just can't solve it in a tractable way, right? And so then I spent most of my PhD years trying to find efficient, approximate algorithms to solve that particular mathematical models. I show up at McGill, I know how to do that very, very well, right? They gave me a PhD for doing that, and now they're giving me my own lab, access to some fantastically talented students. And from that point of looking at sequential decision-making problems, I had the full freedom to branch out and target problems in a wide array of different applications. So in the last few years, I've worked on, with colleagues at the School of Medicine at McGill University on a number of problems trying to apply that very same type of sequential decision model that we use for robots to cases where we were trying to do optimal treatment design. So it turns out people who have a chronic illness often require a sequence of different treatment decisions, right? What's the dosage, what medication, when are you going to give it, in what combination? And these sequences of decision contain a lot of uncertainty. We don't quite know how you're going to react to a particular drug. And there's also a lot of co-effects between the different actions. So the models that I had developed for robotics turned out to be very rich decision-making models for optimizing treatment strategies, whether it was for neurostimulation devices for the treatment of epilepsy, for adapting radiation therapy for patients with cancer, and more recently working with people who are interested in developing new treatment for diabetes and trying to develop essentially artificial pancreas systems for treating diabetes. And so from this expertise in sequential decision making, in particular efficient algorithms for this problem, I could branch out and work with a large number of people just on the healthcare side. Of course, I didn't give up on building robots. I moved from developing the nursing assistant robot, which I'd done in my PhD days, to developing wheelchair robots. And so we've been building a number of robotic wheelchair systems in our lab where we take a commercial power wheelchair directly from the manufacturer and we load it up with sensors and computer power and control boards and so on so that the wheelchair can actually move completely autonomously. And we're also exploring more recently a few other applications, either in education, marketing, resource management, and so on. I regularly have some interesting interactions with other people on the industry side who have some nice decision-making problem that they've found in their industry, and they come to see us to do some partnership in terms of trying to tackle them. So let me give you a little bit of a view on this smart wheelchair project which we've built. This is the robot itself. If you're ever on McGill campus, it's in McConnell Engineering Building. It's usually on the first floor in our lab. But once in a while, we take it out into the real world. We have a partnership with a mall here in Montreal, and it's called basically the Living Lab, the Mall Living Lab. I don't know if some of you recognize that particular mall. It's Alexis-Nihon Mall. And we have, through some understanding with the mall owners, access to the site for doing field testing, deployment studies, and so on. And so in this case, the wheelchair is autonomously controlled because we've built a map of the environment using the laser rangefinders. Using that map, the robot can apply localization algorithms to figure out where it is in the map at any point in time. There's a touchscreen interface where the user can select the next destination, and then the wheelchair navigates autonomously all the way there. We hope that it doesn't run into obstacles. We don't just hope, we develop the algorithms to make it so. And so the wheelchair has the ability to autonomously stop when there are some obstacles in front of it. Some of this is still in development. One of the things that we're really looking at right now is how to distinguish what are real obstacles versus objects that should be approached closely. So in some cases, we want the wheelchair to be able to get close to a table, to a wall, to another person. These should be always considered obstacle. So how do we automatically detect those things that are obstacles, those things that we should approach, and what's the right strategy to approach them in a way that is not dangerous for the person on the wheelchair? We're also looking at how to navigate in small, tight spaces. Getting in and out of elevators, bathrooms, things like that can be very challenging for people who don't have very fine manual control. So can we get the wheelchair to apply these maneuvers automatically is another very nice challenge. So through this platform, we can actually take the big robotic problem and decompose it into smaller problems. And that's how various students in the lab get involved on one specific part of the problem. The one you're seeing illustrated over there is one of the latest that we've been working on, is getting the wheelchair to follow a group of people. So automatically detecting where the people are, as well as doing the closed loop control such that it follows the target over time. Let me tell you about one of these specific projects, which was developed by a master's student in my lab. Bong-Joon Kim did this work. He was an undergrad at University of Waterloo, came to my lab to do his master's degree, and now is a PhD student at MIT. And he had a really interesting question in his thesis that he looked at, which is this question of how do we do navigation when we're dealing with crowds of people? Most of the classic algorithms in robotics for path planning assume that you have an empty environment, or at least you know where the obstacles are. They're static, they're not moving. And so we use algorithms like A*, for example, to figure out what's the right path through the space to get from the current location to the goal location. Most of the time, our robot is deployed in a shopping center or a university building. There's a lot of people walking around at any point in time. So how can we get a path planning algorithms on this robot that is able to socially follow conventions, right? Don't drive up right up to a person and then stop, but skirt around people as they move, try to estimate where the people, we call them dynamic obstacles, where the people are going, what they're doing, and use that to affect the control behavior of the robot. And so this over here is a short first-person video taken from the wheelchair after Bong-Joon had completed his work, after he had done the implementation of what we call the social navigation algorithm. The AI system is controlling this completely using information from a Kinect sensor. So the Kinect gives it a point cloud of the obstacle in the environment. It's breaking up that point cloud into local segment, right? What's going on to the left, to the front, to the right. It's trying to estimate the density of people in each of these locations, as well as the motion direction. So if people on my right are all going in the same direction as I want to go, maybe I should join that flow. Whereas if people on the right are going in the opposite direction, then maybe I should join the flow on the left. Should I be skirting the wall? Should I be just diving through the crowds and hope that the water is separate in front of me? So this is all the kinds of questions that he's using. And in particular, he used an approach called imitation learning. There's a lot of interesting research that's been done on this in recent years, looking at, can we take an expert, ask the expert to control the robot, and then learn the expert's behavior, in particular a function that maps what we're seeing in the environment at a particular time to what the expert did. And so in this case, we had someone come in, drive the robot through the crowd for a little while, and we gathered all of this data, and then we applied imitation learning to learn that function that tells us, matching from characteristics of the environment to the choice of action from this expert controller. And this is the function that we deployed. So the segment that you saw was all autonomous driving from the wheelchair, but it had been learned by observing the strategies of an expert driving through a crowd. Of course, social navigation doesn't always mean avoiding people, right? Sometimes, as I mentioned, we want to get close to them. So since then, another student in the lab, Angus, has been working on developing algorithms such that robots can follow people. We didn't do this only on our wheelchair robot, we also did this on a field robotics trial. In this case, the little yellow robot down there is developed by our friends at ClearPath in Waterloo, very nice robotics company. And they have a laser rangefinder on top, and using that laser, we can actually automatically detect the legs of the person in front. We can do prediction of where those legs are going. We're using the common filter approach for doing that. And then we do closed loop control to actually get the robot to follow over time where the person is going. So on the right, we see what the robot is seeing, and on the left, there's camera image of what's actually going on in the field. And we have some nice demonstration when one person is crossing in front or behind the other, and the robot can actually keep track of the guy with the green shirt all the way through. And we've done loops with over hundreds of meters where the robot can actually go without losing the person. So now we're testing that same approach with our wheelchair robot in indoor environment and trying to get some results. We're talking to some people at the Jewish Rehabilitation Hospital here in Montreal who are very much interested in using, they have no robots, they don't care for robots right now in their clinical practice, but they have the need to precisely measure where people are moving, how they're moving, as part of the rehabilitation treatment for stroke patients. And so in that context, we actually are trying to deploy just our algorithms. We just bring the laser, we don't bring the robot, we just bring the laser rangefinder, and we can estimate the trajectory of a person who suffered a stroke, and they can use that information in their clinical training and clinical assessment. Maybe just one word about the work that we've done with some of the researchers at the Montreal Neurological Institute. There's a fantastic research group in epilepsy over there, and in that group, they have started looking at neurostimulation technique. So you apply electrical stimulation to the brain, and the hypothesis is that by applying stimulation in particular location and at particular timings, you can actually disrupt the neural firing enough that you can stop or prevent epileptic seizures from happening. They're already doing this in an animal model, and when we started collaborating with them, the question we were asking is, can we modulate the timing of the pulses as a function of the EEG, real-time EEG recording, to decide when to apply the stimulation, when not to apply the stimulation, to get more efficient behavior. And so in that sense, we've done some experiments with animals, in vitro slices, where we've actually shown that through this trial and error learning approach, a learning approach similar to what we use for figuring out how to drive a robot through the crowds, we could actually efficiently disrupt seizures more efficiently than if you didn't have the EEG information in the loop. So that's just a taste of the type of things going on. In general, there is a wide spectrum of application, but there's a core of theory and algorithms that's driving the type of research that we do. In the case of my lab, it's mostly how do we design these AI agents with this combination of decision theory, probability theory, and so on, with a lot of applications in robotics. I don't do very much of that work on my own. There's a huge team, mostly grad students, a lot of undergrads as well, who come spend summers with us, who help with this. This is the people at the Reasoning and Learning Lab who did some of the work that we're showing out here. Some of your other speakers that you've seen this week, Monica, Julia, also spent a couple of years in our lab and are now working in the industry. And so I think there's a good exchange. A number of these have graduated over the last few months, and there's new students coming in. And I'm going to finish with maybe one point, which is we don't always deal with very practical problems. Once in a while, there's a lot of much broader question on which we're called to comment. Some of you may have seen some of the news articles coming on in the media these days. People are calling for more interrogation of where AI is going, what is going to be the impact of AI on our lives, and I think there's some very interesting societal discussions to be had. We don't do this necessarily directly in our research, but that's another aspect of the discussion that is going on between academia, industry, and society as well, on which we've been asked to comment over the last 2 years. I'm happy to talk about some of this offline or during questions if some of you are interested. Thanks very much.